Alright, so starting here, let's find the x values where f double prime of x is 0 or undefined. Discuss the concavity of the graph at x, f of x equals x to the fourth minus 4x cubed. Alright, so what's our first thing that we're going to do? Find the first derivative. Okay, so f prime is what? 4x cubed minus 12x squared. Good. And what's the next thing we do?
Find the second derivative.
Find the second derivative. Okay, so f double prime of x is
squared minus 24x.
Okay, so we've got that. Is there anywhere where that's undefined?
No.
No, it's a parabola. Okay, it's a parabola. So the next thing we're going to do is,
Equal to 0.
yeah, set it equal to 0. And then when we solve that, we take out a 12x and we get x minus 2. So x equals 0 or 2. Okay? So, using the table here, that 0 and the 2 are going to kind of be the boundaries here. And the intervals we have are the intervals where x is less than 0, x is between 0 and 2, and x is greater than 2. Okay? So now we have to pick some number within those ranges. Alright, so we could try -1 here, we can try 1 here, and we could try 3 here. If we plug in a -1, what's the sign of our answer for the second derivative?
Positive.
It's positive. We have a negative times -3. Okay, and we get a positive. So what does that tell us about our concavity?
Concave up.
It's concave up.
Do you plug back into the second derivative?
Yes.
Okay.
Just like we would when we were trying to figure out increasing and decreasing, we plugged our test values into the first derivative. If we're trying to determine concavity, we need to plug the test values into the second derivative. Okay? So now if I plug in a 1, I have 12 times 1 times -1. So that's negative. So I'm concave down.
So we do with max, right? At 0.
No. That's actually what we're going to be looking at. These values, 0 and 2, do not give us max and min points. They actually give us what this lesson is about, the points of inflection. And then we'll talk about max and min points when we get to the second derivative test. Okay. Like we said on Friday, that whole lesson was called second derivative test. That was really the foundational stuff to get to what we're going to end with today. Alright, so now we have x equals 3. 12 times 3 times 1 is all positive. So that's concave up again. Alright. Now, what are these points 0 and 2? Okay, we see here that the concavity changes at 0 and then it changes again at 2. The points at which the concavity changes are called points of inflection. That's a term that you should know. Okay? Now, one thing about this is that the tangent line to the graph must exist. It has to be an actual point on the graph. Alright? And also the first derivative would need to be defined at that point. Okay? But here's the thing, if you're going down through looking at first derivative first and then second derivative, it should be pretty obvious if it's not. Okay? Now, this is one of those points where the tangent line does something a little bit odd. Okay? You can see here we have 3 different diagrams of what you might see with a point of inflection. Alright? On the left-hand side of this first one, where we have the point of inflection right here, okay, it's concave upward, and then concave downward to the right. You'll see the tangent line actually passes through the graph. We've seen that one other place, and that was when we had a plateau point, okay? And that's actually one kind of feature of a plateau point, is that a plateau point is also a point of inflection, okay? Not all points of inflection are plateau points, but all plateau points are points of inflection, okay? So if you have a horizontal tangent, that's a plateau. It will be a point of inflection. Of inflection. That can help you, especially if you have one that may be a little bit challenging to solve, where the second derivative equals 0. If you already found all the critical numbers and found that one of those gave you a plateau point, that'll tell you one of the values that'll make the second derivative 0 as well. Okay, so keep that in the back of your mind. Also here we have a place where we have a vertical tangent. Again, it's concave upward on the left, concave downward on the right. We have a change of inflection, okay? Yes?
Do you understand, just looking at a graph, it's downward or upward? When the slope is increasing, it's upward. When the slope is decreasing, it's downward? Is that
Yes. When the slope is increasing, not when the slope is positive necessarily, it's when it's actually increasing. So you'll have to draw a couple of tangent lines. And there we went from negative to 0 to positive to even more positive. It's increasing there. We also said another way that you can tell is when it's concave upward, the graph is sitting on top of the tangent lines. When it's concave downward, like over here, the graph will be underneath the tangent lines. Okay, so that was another way of being able to tell whether it's concave up or down there.
And if it's a negative, we would say the slope is increasing when it's getting closer to 0? Or does it matter if it's below the x-axis?
Doesn't actually.
Yeah, I don't think that doesn't make a difference here. Alright, so now that we've actually done that, you can see here on the graph, this is the graph of the function that we just worked with, okay? Determining the points of inflection was with our warm-up. At 0, which ends up being the point 0, 0, if you plug it back into the original function, you can see we have a change from concave upward to concave downward. And then right here at 2, we have a change from being concave downward to being concave upward. Okay? If you think about this, it makes sense. As you approach a minimum value, at one point we're starting to go downhill here between 0 and the end. Okay? It's going downhill faster and faster, but at some point, if we're going to turn around and go back up, we got to start slowing down. That point of inflection is kind of the moment when we decide we're going to try to pull up out of it. All right, think of like the old movie where the pilot falls asleep or gets knocked out and the plane's in a nosedive. All right, that's here between 0 and 2. And then he wakes up and he grabs the stick and pulls back. That is the moment, that moment is the point of inflection. And then he pulls out of it and goes back up. Alright? That's kind of the idea here. It has to occur before a change in direction can occur. Just like if you are running and you want to change direction, you've got to slow down and come to a stop before you can move. You got to stop accelerating, start slowing down, and come to a stop and change directions. Right. All right, so here is a definition or a theorem for points of inflection. If f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime of c does not exist. Okay? That's what we just saw. So let's get to the actual second derivative test. Okay? The actual second derivative test. What does this test say? Okay? This is a test. If you remember, we had the first derivative test, and the first derivative test told us whether those critical numbers gave us max or min points or plateau points. Okay? The second derivative test will also tell us if we have a max, a min, or a plateau point at one of those critical numbers. Alright, so basically it says this: if the first derivative equals 0 and the second derivative is positive, then f of c will be a relative minimum. Okay? In other words, put this in our language. Okay, if f is concave up, when f prime equals 0, okay, that point is a min. We could say a relative min. Okay? That's what the second derivative test is saying. Alright? Here, if f prime of c equals 0, and the second derivative is negative, then that value of c gives us a relative maximum. Okay? So if the function is concave down when the first derivative equals 0, that point is a maximum. Alright? And if you think about it, it makes sense. To be a min, it's got to be arching up like that. If it's a max, it's got to be arching downward like that. Okay? So this is one of those things that kind of makes sense, but notice here, this only applies when f prime of c equals 0. So we wouldn't use this for the ones where the critical numbers that we get when the first derivative is undefined. Okay. An extension of this also is if the second derivative equals 0, that gives us a plateau. So let's apply this here. I already have the drawing of this, but let's go ahead and prove that -1, -2 is the relative min, and 1, 2 is a relative max. Alright, so first of all, if I were to go ahead and find f prime, that's a -15x squared plus 15 x to the fourth, sorry, plus 15x squared. I'm going to factor out a -15x squared, and I get x squared minus 1. So my critical numbers are what?
Plus or minus 1. Plus or minus 1.
0 and plus or minus 1. Critical numbers. X equals 0 plus or minus 1. Okay? So if I plug those values in, I get -1, -2, and
the original, right?
yeah. And the point 0, 0, because I'm actually getting points on the graph. I'm plugging them back into the original function. And then I get the point 1, 2. Okay? So now, let's look at the second derivative. Alright, second derivative is going to be a negative 60x cubed plus 30x. Alright, if I plug in a negative 1, that's going to be a positive 60 minus 30, so that's positive. If I plug in a 0, I get 0, and if I plug in a 1, I get a negative 30. Okay? So, at this first point, negative 1, negative 2, since the first derivative is 0 and the second derivative is positive, what do I have? A minimum, a relative minimum. If the derivative is 0 but it's concave up, that's got to give me a min.
You find the derivatives of the second, or the zeros of the second derivative, it's just going to be the same thing as the first, right?
Well, actually, in this case, the only one we get, we get a couple, I think. Hang on. We weren't asked for concavity, but if I took out a negative 30x, I'd have a 2x squared minus 1. So x would equal 0 or plus or minus radical 1/2.
Oh, so it's different.
So I'd have, the only one that's the same is this 0, 0, because if the first derivative is 0 and the second derivative is 0, I know that that point is a plateau. And then here at 1, 2, since the first derivative is 0 and my second derivative is negative, I have a relative max. Okay?
So those points are the second derivative. Zeros are just telling you where it's switching concavity.
Yes, and actually let me show you this on the graph here, okay? Here we can confirm, looking at it, here's that plateau where the both derivative, first and second derivatives are 0. Here's where the first derivative is 0 and the second derivative is positive. And here is where the first derivative is 0 and the second derivative is negative. Okay? But square root of 1/2 is root 2 over 2, which is about 0.707. Alright, so right around here and here we had changes in concavity. Now this problem wasn't asking for that, but we can give it just for kicks anyways. Alright, so those are the points of inflection. So you'll notice here, we're concave up until we get to here, then we're concave down, then we're concave up between 0, 0 and this positive radical 1/2, whatever that is. And then we're concave down for this little region, or actually for the rest of it, to negative infinity. Okay? Alright, does that make sense? That's the second derivative test. It's a very simple test. You don't have to do a full sign diagram for the first derivative, especially on one like this that it's very easy to get the second derivative of. It can be really, really useful. Alright? Now, here's one. It's a little more complicated of a function. Let's go through the same process. F prime of x is going to be a 1 plus 2 times negative sine of x Okay, so that's going to equal 0 when sine is a half. Okay, so from 0 to pi over 2, where does sine equal a half? Pi over 6 and 5 pi over 6. Good, first and second quadrants. Okay, so in this case we only have 2 points, pi over 6 something, and 5 pi over 6 something. Okay. If I go ahead and plug those in, cosine of pi over 6 is root 3 over 2. So that times 2 is a root 3. So I've got pi over 6 plus root 3 as my y coordinate. And then if I plug in 5 pi over 6, it's going to be 5 pi over 6 minus root 3. Okay? And we can just leave the coordinate like that. We don't have to figure out it as a decimal. Okay? So now, what's the sign of the second derivative? Well, the second derivative isn't too hard to find. Derivative of 1 is 0. Derivative of a minus 2 sine x is a minus 2 cosine x. So now I plug in pi over 6. If I plug in pi over 6, cosine is positive, so negative 2 times a positive is negative, which tells me that that point at pi over 6 is what? A relative max, okay? Relative max. And then if I plug in 5 pi over 6, cosine of 5 pi over 6, it was negative 2 times a positive root 3 over 2, which was negative root 3. F double prime of 5 pi over 6 is a negative 2. Second quadrant, so cosine is negative. So that's a positive root 3. You don't really need the value as long as you know what the sign is. Okay? So that's a positive, which means what do we have there?
Relative min.
A relative min. Okay? Not too bad, right? All right. So the question is, how do we get the points of inflection?
Yeah.
Well, now that we know, if I wanted to actually get the points of inflection, I would set this equal to 0. So if negative 2 cosine x equals 0, then that means cosine has to equal 0. So x has to be pi over 2 and 3 pi over 2. Right?
Yeah.
Okay. So then I would simply plug those into the original function.
And those are your points of inflection.
Points of inflection are pi over 2, and let's see, that would be cosine of pi over 2 is 0, so it would be pi over 2 pi over 2. And 3 pi over 2. Well, thankfully cosine of 3 pi over 2 is 0 again, so it's 3 pi over 2, 3 pi over 2. I just plug it back in the original function.
Aren't the first and second derivative tests giving you the same thing?
They do.
So which, does it matter which one you use?
No,
Okay.
not really. It's just like in this case, I didn't have to set up the whole number line and test all the different intervals to see increasing, decreasing, increasing, decreasing. It was very easy to find the second derivative, and then I just plugged the two numbers into the second derivative.
Yeah.
Okay.
So pretty much you can do it if you have a min, it's going to be concave up and max is going to be concave down.
Mm-hmm.
Unless it's undefined.
If it's undefined, you got to use first derivative test. If it equals 0 and then it equals 0 again for the second derivative, you've got a point of inflection, or you've got a point of inflection, which is a plateau point.